Hi, welcome to Rotational Motion. I'm going to do a series of videos using rotational motion, and in this video, video 1, I'm going to do all rotational kinematics. So if you use the video slides, you'll see that I'm going to solve the first 4 problems in this video. So let's start with the first one. So we have a child that rolls a ball. So here's our ball, and they roll this ball to another child, which is 3.5 meters away. We know the ball has made, I'll put this over here for R, it's made 15 revolutions. The question is, what is the diameter of our ball? Okay, so if you think about what this means right here, revolutions, one revolution, when this thing turns, you know, if I go here and I follow it and I trace it out, it's going to cover 2 pi r as a linear distance. So that's for one revolution, but if I have 15, what we're going to do is basically take this and multiply by 15 because we have 15 of these. So from that and the total distance, so I'm actually going to write this like L. This gives me the linear distance, okay? So if we want to know how, what the diameter is, we can actually relate this to the linear distance, where L is actually 3.5 in this case. We can solve for R, and we have 15 revolutions. So the way I'm going to set this up will be as follows. I know that when we make 15 revolutions, I will cover more or less in one revolution. I'll go 2 pi r, and the total distance of that will be 3.5. Because then the revolutions will cancel and we're left with r. So r is going to equal to 3.5 meters divided by 15 times 2 times pi. So basically I could have simplified this, but basically you saw that all these came down, and that did too. So when I solve this out, 3.5 divided by 15, 2 pi, I get a radius of 0.3037 meters, but it wants that diameter, and that's twice the radius for the diameter. So if I multiply by that by 2, I get 0.07 meters. So more or less the radius, or the diameter, is 7 centimeters. So that's what we figured out. From here to here is 7 centimeters. So that's question number 1. Let's go on to number 2. I just basically cleared it. Question number 2. A bicycle wheel with tires of that diameter, so I'm going to convert that automatically into meters, plus diameter. Travels, I'm going to convert this immediately into meters, so 8,000 meters. How many revolutions did the wheel make? So kind of like the same idea, we're looking for revolutions. Remember that in one revolution, we'll go 2 pi r, if you will, for a linear distance L. So in this case, we're going to see how many revolutions we make when we go this distance, but I'm going to make that into a radius. Now you can actually leave it as diameter and take out the 2 pi, the 2 that also works, but I personally like working with a radius instead. So this is a radius of 0.34 meters, like that. So essentially what I'm going to do is solve for revolutions. So now remember what we did earlier too, is that the number of revolutions times this will give us our total linear distance. This is for one cycle. But we're going to have many cycles. our revolutions. So that's why we need to multiply it by this. So you can call this, number of revolutions. So if that's the case, I'm solving for basically this part, which means that the number of revolutions that I'm going to make is going to equal to let's see. Oh, I see. Actually, I have to invert this. Let's do that. I'm using the same relationship, but I want my revolutions to cancel out. So it's actually 2 pi r over 1 revolution. There we go. Because then my revolutions will cancel. Perfect. Eventually. So what we have then is, let me just take that out, is we're solving for this. That's what we're solving for. So this is essentially 1. And I get rid of this by dividing both sides by that. So the number of revolutions is going to equal to L divided by 2 pi r, like that. Basically the total distance by the number of circles. Remember, this represents the number of circles. So what we get is we're going to get 8,000 meters like this, divided by 2 pi, and then our r is 0.34 meters like that. And when we solve this out, 8,000 divided by 2 divided by 3.14. Oops, 8,000. We get 3,746.72 revolutions. So that's how many revolutions this will make over that distance, which is many because this is very far and this is actually not a big radius. Well, it's half a meter, so it's a pretty big wheel. But more or less, that is our official answer right there. Okay, let's try the next problem. A wheel accelerates uniformly from this to that in that time. How far did the point on the wheel have traveled during that time? So let's see. We have a wheel diameter once again as 0.33 meters. Then we have an acceleration between RPMs. So why don't we get those? We go from 240, so that's our initial RPMs. And our final is 360 RPMs. So, and we do this in 10 seconds. 6.5 seconds. I don't know where I got time from. Like that. How far did this travel over time? So essentially, we're looking for theta, and then we can actually go into literally the length of that. So let's calculate these things. So as always, these have to be converted into radians per second. So let's do that. So in 1 revolution, there is 2 pi radians times in 1 minute. There's going to be 60 seconds, so we'll do that quick. 240, 2 pi, over 60, gives me 25.12 radians a second. And the 360 is going to be the same conversion. This is a 2. There we go. So 360 times 2 times pi divided by 60. I get 37.68 radians a second. So when I see, so this would be a diameter, and a radius for later, but I see these three things. So this makes me, makes me think of an angular acceleration. And then we can go, let's see, I'm trying to think if I can do this without, oh, we do have the time. So it looks like we could do, no, we can't because we need angular acceleration. Okay. Oops, sorry, I didn't mean to do that. There we go. Oh, I know what we can use. We can use this one. 1/2 omega I plus omega f times t. There you go. Where we can find that. So this will be 1/2 omega I. I'm sorry, let's just put omega I in there. So omega I is going to be the 25.12 radians per second, plus the f, 37.68 radians per second, times 6.5 seconds. So let's calculate that out. So what I get is, I get this as 204.1 radians. So how far did we go? Well, remember that we could actually, if we know r, and we multiply by L, I'm sorry, by the angle, we can get L. How far did we go, right? So this will be the following. So R, we can actually get up here. So I'll put that, R is going to be the diameter divided by 2. .165 meters, like that. And then this is our radian measure, like that. So we will get 0.165 meters times 204.1. So when we radians, multiply these two together, we get a distance L of 33.67 meters. Now the radians go away, because radians is more of a kind of a number. It's not necessarily a unit. So this just represents how many circles we made. So we made, according to this radius, a certain amount of circles. So basically we can, quote, ignore the units right here. So that's why we're left with this. And that's how far we went. So that's one way we can do that problem. Alright, let's do the last problem. Tires make 65 revolutions, and then it goes from there to there. What's the angular acceleration, and how much time is required for this to stop? So let's take a look at that. Alright, so we have 65 revolutions. We can convert that into radians. We have 95 kilometers per hour, which we can convert to, eventually we would like to convert it to radians per second. But that's an initial. And then we have a final, which is 45 kilometers per hour. Again, we're going to convert that to radians per second. And we have the diameter of the tires, once again, 0.08 meters. What is A? Okay, looks like we're going to run out of time. I thought I'd cover all of it, but that's okay. In the next video, I'll finish up this problem.